let's start today's class. Please check your attendance on the blackboard. I found some students emailed me, and then they forgot checking the attendance on the blackboard. But this is the automation system. So actually, in order to prove your attendance, then you need to also submit some evidences for your attendance. Okay, so please do not forget checking your attendance. Okay. As I mentioned, I will not manually check your attendance. Okay. Okay. So let's start today's class. Okay, so in the previous class, we learned about the Boolean algebra. Okay, so what is the Boolean algebra? So it's like the normal algebra. The Boolean algebra is handles the equation, actually the Boolean equations. The which means that the Boolean equation handle just the true or false values. Okay, so that's why the systems use the Boolean equation, because these systems also handle only two kinds of values, zeros and ones. Okay. So, and then in the previous class we learned several axioms and then theorems. Okay. So I said that it's very similar to the normal mathematics axioms and theorems. Actually, we don't need to prove axioms. Okay, I found some here. There are some high school students. Unfortunately, the April Fool's Day is Saturday. Okay, but okay. So. And then theorems. We can prove some theorems using several axioms. Okay. And then also the 5 theorems are very obvious. And also it's obvious. And also these theorems. So if we see the theorems, and then we can find that these theorems are very similar to the normal algebra theorem, but only difference is this one. Okay, this is because I mentioned that you are very familiar with the distributivity theorem, but it's not familiar, right? It's different from our normal algebra theorems. But I mentioned that this is just or, not plus, not and. So, and then actually the property of OR gate is actually similar to the property of AND gate. Okay? There is no difference. The only difference is the result of OR gate and AND gate. So actually we can rewrite this equation like this. So OR can be also distributed to the different forms of AND gate. Okay, and then so we can prove the several theorems using these two methods. Method one is the very brutal method, the brutal force method, which means that we can just write all possible input cases, and then also we can calculate all outputs from these all possible input values that we can prove the two, the left term and then right term are equal. And then method 2 is that we can use the theorems and then axioms we learned in the previous class to prove the several other theorems. Okay. So now here, combining here. And then I also explained the Morgan theorem. And then actually I said this is it's an important theorem because The Morgan theorem is the unique theorem in Boolean equations. Okay, and so which means that we can change this AND gate into several OR gate, but it means that the output is the negation of output is changed to the negation, the inversion of input. So the inverse process is the same. It's called the dual. Okay, so we can apply the same theorem to the OR gate. Actually, so I will mention the Morgan theorem in today's class again. Okay. Okay. Those are what we learned in the previous class. Then what? Why did they learn several theorems and the axioms of Boolean equation, the Boolean algebra? Okay. So actually, when we learned about the Boolean equations, we learned about the SOP form and COS form. And then what we learned? What did we learn? We learned every truth table can be represented using SOP form or COS form, right? So we can represent all truth table and every truth table, the result of binary inputs. Then we can represent the truth table using the SOP form and then QS form. So in the SOP form, we can use the min terms, right? And then in the QS form, we can use max terms. But these Boolean equations are not optimized. So what does that mean? What does optimization mean in the system? What's the optimization? Okay. So in Korean, it is called 최적화, right? And so optimizing or optimization. So what does that mean? Why do we need to optimize a certain system? Because optimization, so we optimize a certain system to improve performance, also to reduce cost. Then what is the performance? The first factor is performance. That is good. Which factor is related performance? Time, right? So I mentioned that. So if we can run some programs or we can generate the outputs from the input data more quickly, then we can say that, oh, this system is a better system. So if in the if we just consider performance of the system, so which means that the performance of this system is higher, is high. Okay, and then so the performance is related to the time. So which means that actually it's related to the delay of a system. Then what is the cost? Why do we need to optimize a circuit? Why do we need to optimize a digital system? It's enough to reduce cost. Then what is related to the cost? So we can consider power. Okay. Also we can consider the number of transistors. What does that mean? So it's the so this is the example. So the Y equal A exclusive or B. And then we can also rewrite this function as like AB plus this is not true. Not this one. B, from bottom B, this to B, okay. So what is equivalent? Actually, this is the same equation. A exclusive over B, and then A, B bar, A and B bar, or A bar and B. So these equations are actually the same equation. What is equivalent? This equation uses only one gate, exclusive OR gate, and then usually exclusive OR gate includes 4 transistors. How about this? This equation includes 3 gates, right? So one AND gate, and then one OR gate. So it will require 3 gates. Also, actually, not to implement AND gate and OR gate, so we can also consider NOT gate here, but just to do not consider the NOT gate. So let us assume that this equation required only 3 gates. But in order to implement the AND gate and OR gate and AND gate, actually we require 6 transistors, and then 6 transistors, and then 6 transistors. So actually, in order to implement this Boolean equation, we require total 18 transistors, right? And then this is the 4 transistors. So the cost is also related to the number of transistors. So if we divide this equation into this optimized equation, then we can reduce the number of transistors for implementing Boolean equation. So that's why we need to simplify Boolean equations using axioms and theorems we learned. Okay. So let's see the some examples. So this is the very simple example. So as you can see, you can find the this equation y equal a bar and b or plus a and b. So this is not an optimized equation. Why? You can rewrite this equation like y equal b. Then how can you know? So we can apply some theorems or axioms to simplify Boolean equations. So actually, this is very simple. If we apply combining theorem, okay, so we can rewrite this Boolean equation like a bar plus a, right? So, and b, and then the a bar or a equal actually it's 1. Okay, so 1 and b is also b. So actually, this equation represents y is identical to b. So actually, we don't need to use AND gate to implement this equation, right? So b requires just a wire. So y is just connected to b. But in order to implement this equation, as you can see, we require 3 basic logic gates: AND gate, 2 AND gate, and 1 OR gate. So we can optimize Boolean equations using theorems, axioms. So this is another example. So it's a little bit tricky because so A is you can see this is the Boolean equation. Then you are requested to simplify this equation. And how? So actually, we are not familiar with this theorem, right? So actually, in the real mathematics, this is 2a, but in the Boolean equation, a or a equal a, and it's obvious actually, right? A or a is a, and then a and a is also a. So But in order to simplify this Boolean equation, we need to use this idempotence theorem. Okay, so A plus A equal A in Boolean equation. So A multiplied by A equal A. So which means that we can repeat this term A, B, C. So the A, B, C plus A, B, C. Then we can apply the associativity theorem. So because for this term, we can find that no, actually, so we can focus on this term. So associative means that we can just use the bracket to rewrite this equation. So we can group these terms, and then also we can group these terms. Okay. Then we can also apply the combining theorem. So in this term, I will use actually the color is different. A, B is a common terms, so A, B, and then we can find that in these terms, we can find B bar and B, right? So, the B bar plus B is 1, so we can remove first. Okay, so result is the AC. So we can rewrite these terms like A and C. Also, we can apply the same theorem to the ABC and the A bar BC. So this is the common term, and then we can find A and A bar. A plus A bar equal to 1. So we can rewrite the system like the BC. So actually, this equation can be rewritten like AC plus BC. So as you can see, this is simplified form, simplified equation. Okay, you can apply the theorem like this. This is another example. A plus A bar P equal A plus P. Also, how can you apply this? How can you simplify this equation? So if we just see this equation, then you may be, it's not easy, right? It's a little bit tricky, because it's not similar to the real algebra. Okay, but we can apply several theorems for this equation. So firstly, we can rewrite the A as the A plus AP. Okay, this is the covering theorem. Okay, and then we can also apply the associativity. Okay, so which means that we can group these two terms. Okay, this is very so we learned in this class, right? So actually, this theorem is frequently used in the Boolean algebra. Actually, this term is frequently used. So AP plus A bar P, we can remove A. Okay. So this is the AP. So method 2 also we can apply the different theorem to simplify. Actually, to prove this equation. So we can simplify this Boolean equation. Okay. Then, so actually, you may think that actually the normal algebra is very familiar to us. So we can apply some very familiar theorems to simplify our equations, right? But the Boolean algebra it's simpler than the normal mathematics algebra. But actually, the properties are a little bit different. So actually, we need a practice to be familiar with the Boolean algebra. Okay. Okay, let's think about the De Morgan's the theorem. So this is the example. So by applying the Morgan theorem, you are requested to rewrite this Boolean equation. Then how can we apply the Morgan theorem? So what can you observe in this equation? So we can observe this long bar. Okay, what does that mean? You can observe this long bar. So here, okay, so we can start from this one, which means that from outside to the inside. So you can find the outside bar, the most outside bar here. Okay, this is the longest bar. So what does that mean? Actually, so so this is the multiplication for this longest bar, the outside bar. So we know that this equation has two terms. So what are those terms? These terms and these terms. Okay. And then when we apply the Morgan theorem, the multiplication, this is the AND gate, is changed to the OR gate, the addition, and then OR gate is changed to the AND gate, the multiplication. But in this equation, you can find the two terms here, and then you can find multiplication here. Then how can we rewrite this equation? So firstly, we can apply the Morgan theorem. So if we rewrite this equation, it looks like the AND gate, right? Okay, so this is the AND gate. I said that there are two terms here. One term is here, this is another term, and then this is AND and the inversion. So it is NAND gate, right? And then by applying the Morgan theorem, we can change this NAND gate into the inversion of inputs, okay, and then OR gate, right? So how can you rewrite this equation? We need to invert this term, right? Invert A plus B, C, and OR. And also we need to invert this term. So this is C, right? You understand? So we apply the Morgan theorem. Also, actually, the invert C is the C. Actually, it's a C. So it's optimized. It's a C actually. And then how about this one? We can also apply the Morgan theorem to this equation. Right? So what is why? You can find the bar here, long bar, another long bar. Also, this is the OR gate. Then, how can we rewrite this one? It's the A bar and D plus C, right? Also, this is removed the invert of the inversion. So this is the A bar and the C plus C. And then we can apply another theorem to simplify this equation. So this is the result of the simplification and then application of the Morgan theorem. Okay. So just remember that we can start from the outside. So if we can find the long bar, the inversion, this equation, and then we can start from this outside inversion to the inside of the inversion. Okay. And then this is another example. You can also apply the same rules to the this Morgan theorem. So which means that we can apply the Morgan theorem and we can rewrite this Boolean equation. Okay? So like this. So actually, if we use but currently you may not be familiar with the Morgan theorem because this is a little bit different from the normal mathematics algebra. But if you can practice, then you can. I believe you can easily rewrite this equation using the Morgan theorem. The important thing is that we can start from this outside bar to the inside bar. So we can define a term in this long bar, and then we can apply the Morgan theorem. Okay. Okay. So now let's go to the next slide. Okay, so now we will learn how to implement Boolean equations using logic gates. So which means that we can implement combinational logics, okay, from Boolean equations. So what does that mean? Actually, in the previous class, we learned about the basic logic gates such as AND gate and OR gate. And then I also mentioned that the Boolean equations can be represented using these basic logic gates. So in this class, we will learn how to implement this logic using gates. So let's start from the example. Let's start with the example. So you are requested to build a digital circuit, the digital logic from this Boolean equations. This Boolean equation, how? Actually easy, right? You can, so we already know that this means multiplication means, and then the plus sign, the addition means or. So which means we can just implement, just write so this figure is called schematic. Schematic. So using the basic logic gates like the AND gate and OR gate, we can implement this logic very easily. Right? Good. You can just remember that the multiplication represents the OR gate, AND gate, and then addition represent OR gate. So you can find the AND gate here. Okay, this is the multiplication. And then this is OR gate. So it means the plus sign. And then also these are midterm. So B bar is here, B is inverted, and then also the C bar is here, the C is also inverted. Very easy, right? Then also we need to follow some rules for drawing a schematic. Okay. So usually the input is placed on the left or top. Okay. So input starts from this left or top. So actually the signals flow from left to the right or top to the bottom. Okay. These are schematic rules, the normal schematic rules. You can usually follow rules, these schematic rules. Also, output signals are placed on the right or bottom. Okay. And then, as I mentioned, the signals flow left to the right and then top to the bottom because the input is placed on the left and the output is placed to the right. So obviously, the signal flow from left side to the right side or top to the bottom. And then these are node or wires. Okay, so we can say that all these are node at N1 and N2. And then also in order to represent node, which means that we need to connect the output of a certain gate to the input of another gate because the signals flow from left to right. And then so which means that we need to connect the output of this circuit to the input of this circuit. Then we can use wire. Okay. The wire is represented using straight lines. Okay, like this. But it's okay, but usually it's okay, but usually we draw a schematic like this. So horizontal line and the vertical line. And then how can we represent junction and connections? So we can represent, so actually, so this is a very simple schematic, but if we draw more complex schematics, then we need to use many wires, which means that the wires can cross like this, or so on. So the wire can make T junction. So it's also very important rule. So if two wires connect like a T junction, like here, then these two wires are connected. So this is the T junction, right? So this is a wire, this is another wire. So these two wires meet at this point. So and then it generate the T junction. So even though we do not use that here, but you can think that you need to know that does not work. These two wires are connected, right? And it's obvious, right? So this wire ends at this point. So it means that this vertical line is connected to the horizontal line. Okay? So if we use the T junction, so it means that these two wires are connected to each other. And then it's familiar. So and then two wires cross each other, and then if we use a dot at this crossing point, then which means these two wires are connected. And we frequently use a dot to represent two wires are connected to each other. So this is another representation, but in this representation, we cannot find any dot. So two wires cross each other, but that is not located at the crossing point. Which means actually the two wires are not connected. So you need to remember. So you need to remember also in the T junction, even though we do not use a dot at the crossing point, but you need to think that in the at the T junction, two wires are connected. And then if the two wires cross each other, then we need to use a dot to represent two wires are connected. Then if we do not use a dot, then these two wires are not connected. Okay, this is the important. These are important rules. Okay, for drawing schematics. Okay, and then also we frequently use two-level logic. So two-level logic means that we just represent the Boolean equations using two steps of basic gates. So it's an example. So and followed by or. So actually, what is this form? This form is the SOP form, right? Sum of product. The sum of the product, the mean terms. Then how can we draw schematic from this equation. Which means that how can we design digital logic from this equation? That's actually easy, right? We can. So this is the two-level logic. So which means that the output of AND gate is connected to the inputs of OR gate. Okay, and then this is the SOP form. So we can write a schematic like this. Okay, but in the smart way, we can write a schematic like this. So what can you see? So these are inputs. So if you see this equation, you can find some little words. So like A and A bar and B and B bar and C and C bar. And then these returns are generated main terms like A bar, B bar, C bar, and something like that. So we can generate the all literals like A and A bar and B and B bar and C and C bar like this. So we can find the inverter here. And then this is the AND gate, right? So to represent, not to represent this A bar, C bar, C bar, then we need to connect this line to this AND gate, and then this line to this AND gate, and then another this line to this AND gate, right? So you know, this is the T junction. This is the T junction. So this line is connected to the inverter line. And how about this? Two lines cross, but we cannot see any dot here. So this line and this line is not connected. Okay. So which means the input of this AND gate is connected to the not A, the A bar. And then another input, the second input of this AND gate is connected to not B, and the third input is connected to not C, and then we can generate this term in A bar, B bar, and then C bar. And then for the other term, then we can connect the inputs of this AND gate to the literals. Okay, A and B bar. So the output of this AND gate represents this term, and then output of this AND gate represents this term, and also this term. And then by connecting min terms to the final OR gate, then we can generate output Y. So we can represent logic gate like this. And then this is the example, the two-level logic. We can also consider multi-level logic. So two-level logic is the most common form, but because, as I mentioned, we can represent the every truth table using SOP or POS forms. But we can also consider the multi-level logic, which means that we can the signals can pass through multiple logic gates, like more than two. Okay, so as you can see, this is the input and this is the output. The output from input to the output, we can find three logic gates. So this is the three-level logic. But we can consider also this logic gate, this digital logic. Okay. Okay, let's see the example. So this example is the priority circuit. The priority circuit means that the priority circuit represents the location of the first one. What does it mean? So we can find three inputs here, from A0 to A3, and then also we can find the four. We can find four inputs. That's it, four. And then we can also find four outputs here. And then actually the Y3 represents that if the A3 is 1, the y3 becomes 1. So which means that these outputs, the four outputs represent the location of the first one from left to the right side. For example, how about what is the output of this private circuit, like 0, 1, 1, 0? What are the outputs? So this is the left side, and this is the right side. So the MSB and this is LSB. So what is the output of this circuit? What is the first one from left to the right? And then in this figure, the top to the bottom. First one is this one, right? So y2 becomes 1, and then this is the 0, 0, 0. Okay, because so this output represents the location of the first one. Okay. So this is the truth table. Okay. So because there are 4 inputs in this circuit, and there are all possible 16 cases, right? And then what are the outputs? So this is the output. So we can define outputs like this. There are 4 outputs. And then, so as I mentioned, if the A3, so this is the first one. If the first one is 1, then Y3 becomes 1. And then if the A2 is the first one, then Y2 becomes 1. And then so we can apply the same rule. And then if the all signals are zeros, then output signals are also become zeros, all zeros. Okay, this is the definition of a priority circuit. So then how can we implement this the logic for this priority circuit? So which means we first define Boolean equation, right? Right? So it's easy, right? So actually there are 4 inputs here, 4 inputs, and then we can not to make the Boolean equation for y3, then we need to focus on the result of y3 from these 4 inputs. And then we can apply SOP form or QS form to write the Boolean equation. How can we write Boolean equation? So we can, as we learn, we can apply the QS SOP or QS form. But if you see that this most people, actually we can generate the simplified Boolean equation intuitively. What does that mean? We can easily generate the simplified Boolean equation from this first table intuitively, not using SOP form or QS form or Boolean algebra theorems. How? So think like this. So if we just focus on the output y3, then actually the output y3 is identical to the input a3, right? You can use the actually the brute force. And so it's a first method. So if we just write the first table, if we define all possible, inputs, and then we can figure out all outputs from the possible inputs, and then we can observe y3 is actually identical. It's same to the a3. Y3 is identical to the a3. So what does it mean? It's y3 equal a3. That's it. Okay. And how about the y2? white becomes 1, and then only this case, right? So actually, we can, right? We can define this output using a normal sentence. Y2 becomes 1 if A3 is not 1. So A3 is 0 and A2 is 1. Because when I define this priority structure, then this output represents the location of the first one. So which means that in order to make Y2 1, then A3 needs to be 0, and then A2 is 1. It's just simple, right? So we can define the Y2 like the A3 is 0 and A2 is 1. It's very simple, right? So this is A3 and A2. So we can represent the Boolean equation from the sentence, like a condition from the sentence that define the conditions. How about the Y3? So with the same way, so Y3 is Y1. Sorry. How about the Y1? Using the same way, then it's the A3, A2, and A1. How about the Y0? Only this one. So here, this lat is low, so it pops. A3, A2, A1, A0. So actually, this is so easy. So actually, we can easily define the condition and make Y0, and then we can generate the Boolean equation for each output like this. It's the Boolean equation for this output. So, but I want explain about the don't care signal. So actually, so we can, in order to represent the priority circuit, and we can define all possible inputs, and then we can generate the outputs. We can define outputs like this. But we can simplify this two table using don't care signal or don't care bit. So what does that mean? We can, so if we see that this output Y3, then we can know that if the A3 is 1, and then the Y3 becomes 1, regardless the values of A2, A1, and A0. Which means that if the A3 is 1, then if the A2 is 0 or not, 0 or 1, or 0 or 1, or 0 or 1. So regardless of the values of in A0, A1, A2, then Y3 is equal to the A3. Then we can rewrite this part like this, like 1, and then X, X, X. Why? Because it's don't care. So we do not care about the result of is A0, A2, and wait a second. So regardless of the values of A0 and A1, A2, we can rewrite these signals like this. Okay, then we can simplify this truth table like this. So A3 is 1, and then it's a bunch here. Regardless of 1 or 0 of the A2, A1, A0, then Y3 becomes 1. And then also exchange the Y2, so it's a 0 and 1. And then also A1 is done here, A0 is done here. So Y2 becomes 1. So it's simplified. So it's easy to understand. Okay. So where does it come? So 뭐 충전기 있는 사람이에요. 이제 그 USB-C PD 있는 사람 있네. 이게 배터리가 다 됐네. 예? 예. 감사합니다. Okay, thank you. Okay, so Intel laptop, Intel tablet is what is Intel power on my possible. Okay, so let's see the another forms of the two-level logic. So there are several variations of the two-level logic. So we can consider the ANDs followed by OR. So which means that there are several ANDs here, and then the output of ANDs is ORed by OR, and then generate the final output. So which means the ANDs followed by ORs. And so this is actually called the SOP form, right? So we learn. Also, we can consider another form, the POS form. So which means ORs followed by ANDs. So which means so there are several OR gates here. And then the output of OR gate actually it should be like this. Is ANDed and then generate the output. So this is the POS form, and then we can define the two-level logic as the POS form, the OR followed by ANDs. And then we can also implement SOP form using only NAND gates. I will explain later. Also, we can also generate POS form of Boolean equation using only NOR gate. But usually we use the AND followed by ORs, so SOP form. So this is the most common form of the two-level logic. So like this logic, okay, this AND followed by ORs, so two-level logic, and then this is the SOP form. So this is the POS example, right? So it's another two-level logic. The ORs followed by ANDs. So like the SOP form, you can implement the logic like this. So what is different? So we can use the OR gate for the first stage, and then after the OR gate is connected to the AND gate. So we can find that these are max terms, right? So we can give, so this is the Boolean equation, and then we can implement this Boolean equation like this. Then how about only NAND gate. So this is the same example. So you can find the same example like this. So we can implement the logic for this Boolean equation and followed by OR. And then we can convert this logic using NAND gates. How? And followed OR, it looks like this. So this is the AND gate, and then the output of AND gate is connected to the OR gate, right? But by applying, so we can apply the Morgan theorem actually in this structure. How? If we add bubble here and the bubble here, also we can add bubble here and bubble here. So what does that mean? This is a wire and that connects the output of AND gate to the input of OR gate. And then we place two bubbles in this node, in this wire. And then two bubbles is equal to just wire, right? The inversion of inversion is equal to the original signal, right? So we can just add two bubbles like this. Then, what is this? This is the AND gate. And what is this? If we apply the Morgan theorem, map of OR gate can be changed into the AND gate, right? So bubble is here. So it's the NAND of input, and then this is the OR gate. So actually we can convert this part like the NAND gate, right? By applying the Morgan theorem. So actually, this equation, the SOP form, can be represent like using only NAND gate. Okay? So this is the example. It's actually the same example. So this is we can place bubble here, the output of the AND gate, and also we can place bubbles to the inputs of this final OR gate. Right? And it's the same, right? The bubble is here, bubble is here, bubble is here. So, and then this OR gate can be changed into the AND gate, and AND gate. Right? So, by this SOP form can be implemented using two levels of NAND gates. Okay? Why did we learn this? I mentioned that in order to implement the two input AND gate, then we require 4 transistors. But in order to implement the two input NAND, 6 transistors, sorry. In order to implement the AND gate, two input AND gate, then we require 6 transistors. But in order to implement two input NAND gate, then we require 4 transistors. So actually, if we use a NAND or NOR gate, then we can reduce the number of transistors required for implementing this NAND logic. Okay? Because we need to implement the AND gate using NAND gate plus NOT gate. Okay? That's why we require 6 transistors. So we can reduce cost if we use the AND gate only, and if we implement this SOP form of the Boolean equation using NAND gate. Okay. We can also apply the same way to the POS form. So words followed by ands. Also, we can add bubbles like here, right? The bubbles here and bubbles here. Also, we can find bubbles here. Bubble over bubble is the same story, no? So this is the NOR gate, and also by applying the Morgan theorem, this AND gate can be changed into the NOR gate. Okay, so NOR gate. So by using two stages of NOR gates, we can implement POS form. Okay. So there are four variations of the two-level logic. Okay, so let's review the bubble pushing. Actually, we already learned the Morgan theorem, and then we already learned how to push bubbles by applying the Morgan theorem. So this is the Morgan theorem, right? And then we already learned that. So by applying the Morgan theorem, then we can keep the bubble is at the output of the AND gate, and this can be changed into the bubbles in the bubbles on the inputs of the OR gate, and then bubbles is transferred to the inputs, and then the AND gate is changed to the OR gate, and then also this same theorem is applied to the OR is working, the working. Okay. Also, we already learned about the bubble pushing rule. So, this output of the bubble of the AND gate can be pushed into the input of this working. I think this is the Morgan theorem. So we can also the bubble and the input signals can be transferred to the output of the different gate in inverse gate. Not so AND is changed to the OR, and the OR is changed to the AND. This is the Morgan theorem. So then how can we apply the bubble pushing rules? So we can start from the output. So when we apply the Morgan theorem, then in the Boolean equation, we start from the outside. Right. What does that mean? The outside bar. This outside bar represents the y. This outside bar represents the actually the finite bubble. Right. Right. This bar is the represent the inversion. So I also mentioned that bubble represent inversion. Okay. So we can start from the final output. Then we can push bubbles to the input. So we can start from this gate, the finite gate, and then we can apply the Morgan theorem here. Actually, but as you can see, this circuit is the optimized circuit, right? Because this circuit includes the NAND gate, and NOR gate. Actually, we don't need to optimize this circuit. But when we apply the Morgan theorem, then the bubble pushing rules, then we can start from this final gate. Okay, let's see the another representation, X and Z. So actually, until now, we assume that input or output signals have only two kinds of values, 1 and 0, right? But we will learn about the another representations like X and Z. Why? So we are learning about the digital system, and then I also mentioned that digital system has only two values, 1 and 0. How about X and how about Z? Why do we need to learn? Because we are learning about the digital system, and then we can implement digital systems as digital circuit. Okay, but then circuit is the electric circuit. So which means that actually I said that the voltage level, voltage is translated into the digital level 1 and 0. So which means that actually the voltage is the analog signal, and we can represent actually the voltage signal have many different values, many different representations. But we only consider the 1 and 0. Then what is X and what is Z? Actually, so I will explain about the representation X. So, okay, let's start from this example. Is this circuit is the correct circuit or not? Is this a combination circuit? No, because this is the output of the NOT gate, and then output of NOT gate is connected each other. So what does that mean? So when we think about the digital circuit, and then actually we need to know the definition of driver and receiver. So actually driver means this is the output. Receiver represents the input. Actually driver generates the output signal by changing voltage level of output wire. Okay, this is the driver. So actually the driver generates the output signals 1 or 0. Then the receiver receives the output signals from a driver. Okay? So what's the problem? Actually, if you see that this node, that this is wire, this node, then this wire is driven by two outputs, two drivers. Now what's the problem? Actually, this in NOT gate may generate the 1, and then this NOT gate may generate 0. Then what is the value of this 1? We don't know actually. So if this driver, so this NOT gate generate 1, then we can say that this is 1 because actually this NOT gate generates the VDD voltage, so drive the VDD voltage to the output wire. So the same VDD voltage is driven to this wire. So it's the same. If the value is the same, then this wire becomes also 1 VDD. But this is the output, and then also this is 0, because the input is 1 and the input is 0, so this becomes the 0. Then we don't know. We don't know which voltage level is set for this wire, because this is 0 and then this is 1. So actually, this is the incorrect circuit. And then, so this is actually this is called contention. Okay, so contention, which contention means the circuit tries to drive output to 1 and 0. And then this, So which means that actually we don't know the exact output values. Okay? Because the output wire is driven by two drivers. It's not allowed in the digital circuit actually, because when we design the digital circuit, then the output needs to meet the constraint like the BBB to drop. So we learned about the noise margin. Also, we learned about the output allowable VOF and OH. Okay, the allowable output range. So, if the same wire is driven by two driver, it's not allowed, and then we don't know the exact value. So this is called the contention. Okay, then actually this is represented like this. We represent the output of this wire using X, and then X will represent the contention of a circuit, and then it is the actually illegal value. It's not a correct value. Okay, so we can represent the X. Okay, so usually if you observe X in the circuit, then it represents that this circuit does not work properly. Okay, so if you observe X in your circuit, then it represents this circuit is not working correctly. Okay, X means the contention. But we also learned X the previous slide. What does that mean? This one is also X. We also represent the pair using X. Okay. So be aware of this different meanings of X, because we also use X for representing don't care or uninitialized value. Okay? So do not be confused, but we need to understand the meaning of X based on the context actually, which means that if we observe X in the truth table, then it represents this X is the don't care. Okay, but if we observe X in the circuit, then it represents X means contention, so which means illegal value, illegal voltage level, and the X means the wire is driven by multiple drivers. Okay, in a circuit. Also, we can use the X for the uninitialized value. Actually, we will use we will learn about the system variable, and then in order to verify the system variable module, then we need to check the waveform. But if the signal is not initialized, then waveform represent the signal using X actually. So actually, X represents the different meaning. So we need to understand the real meaning of X based on the context. Okay. So X may represent the don't care, or X represent the uninitialized value, or X can represent contention. Okay. But if you observe X in the circuit, like this logic gate, then it represents the illegal value. Which means that this is not a correct structure. Okay. Then okay. And then another value is the Z. The Z means the high impedance. Okay. And then okay, so I need to stop here. I will explain the Z. Any question? Okay, thank you. Thank you. Okay.